In the last lecture, we were looking at dispersion as contrasted with diffusion. Diffusion is the transport of mass, momentum or energy due to the molecular fluctuating velocities. Even when the fluid is at rest, there are fluctuating velocities of the molecules in all three directions. The fluctuating velocity is comparable to the speed of sound through the medium. And these molecular fluctuating velocities will result in a transport when there is a variation. Even though the molecular fluctuating velocities are isotropic, they have equal magnitudes in all directions, there could still be a transport when there is a variation in the concentration or temperature or momentum. Compared to this, convection is transport due to the fluid velocity, and it takes place in the direction of the fluid velocity. The convective flux is the product, the convective flux at a surface is the product of the velocity perpendicular to the surface and the local density, concentration, energy density or momentum density. The fluid velocity field consists of two distinct kinds of velocity fields. One is laminar and the other is what is called a turbulent flow. Okay. In a laminar flow, the velocity is, there are nice straight smooth streamlines. The velocity field at steady state is independent of time, and at a location, if you measure the velocity, it will be a constant. As the Reynolds number increases, there is a transition to a turbulent flow, which consists of large fluctuations in the velocity. Even though the velocity is on average in the flow direction, in this case in the x direction, there are large fluctuations in the cross stream directions, the y and z directions, as well as in the flow direction. And mass, momentum and energy are transported both by the mean velocity as well as by the velocity fluctuations. So, the transport of energy due to the mean velocity is what is called the mean flux. There is also a transport due to fluctuations, and that is what is called dispersion. So, we had separated out the velocity into two parts. One is the average velocity. Okay, we had separated out the velocity into two parts. One is what is called the average velocity. For a statistically steady system, okay, the average velocity is defined as a time average over a time period which is large compared to the time for variation of the velocity or the time for the fluctuations. So, you define an average over this long time period. The average is called the mean velocity, and the fluctuations about the average, that is the velocity fluctuations, represented by primes. So, the velocity Vx is written as the sum of a mean velocity, we are using bar for the mean velocity, plus the fluctuating velocity. Okay. And the concentration flux, for example, is the average of c times Vx. Okay. So, I just told you that the flux is the velocity normal to the surface times the concentration at that point on the surface. The velocity fluctuates because there are eddies, parcels of fluid moving in correlated motion. These eddies, as they move along, they take along with them their concentration fields, and of course, there is diffusion which tends to smooth out the concentration fields. Because of the fluctuating velocities, there will also be fluctuations in the concentration field, and the concentration can also be expressed as a sum of a mean value plus a fluctuating value. The average flux, so the flux is the perpendicular velocity times the concentration field, and the average flux is a time average of this instantaneous flux, where the concentration and the velocity are each separated out into their mean and fluctuating parts. Okay. So, when you do the integral of the mean velocity, you get something that is just the product of the mean concentration and the mean velocity. terms that are linear in the velocity fluctuations will average to 0, because the average of V x prime is 0, the average of C prime is 0. However, you get an additional term which is proportional to the product of C prime and V x prime, that is not 0 in general. Okay. So, there is an additional term due to the product of the concentration and the velocity fluctuations. Okay. The average of the product is not the product of the averages. Okay. To understand that, you just have to take the square of a quantity and you will find that its average is not 0. So, even though C prime average is 0, V x prime average is 0, the product of those two is not necessarily 0. That is the contribution to the flux due to the fluctuations, due to the correlation in the fluctuations. You will get a non-zero value if V x prime is positive when more often when C prime is positive and vice versa, or where V x prime is positive when C prime is negative and vice versa. Okay. So, if there is a correlation, then you will get a non-zero value, and that is the dispersion flux. Okay. It is also called the Reynolds flux, J r. Okay. And I showed you a simple example that a product of two quantities which both have 0 averages, if you take the product of those two, the average in general is not 0. Okay. So, we saw an example of that. Okay. A similar decomposition can be made, for example, for the energy transfer, okay, for heat transfer, for example. The energy flux, the energy flux Q in some direction Q x say is equal to V x times the energy density, rho C p T, for an ideal gas. This is not the average, at a given surface. This can be written as Q x bar plus Q x prime. Therefore, Q x bar is equal to 1 over T average integral 0 to T average dt V x rho C p T, where rho C p T is the enthalpy content in the in that parcel of fluid, the enthalpy density. Now, we can separate V x is equal to V x bar plus V x prime, T is equal to T bar plus T prime. Therefore, Q x average is equal to 1 over T average integral 0 to T average dt V x bar plus V x prime rho C p into T bar plus T prime. And I expand this out as usual, and what I will be left with is just rho C p T bar V x bar plus rho C p into V x prime T prime the whole average, just as we had done it for the concentration field. So, this is the flux due to the mean velocity, and this is the flux due to fluctuations. It is called the Reynolds flux. Q x Reynolds is equal to rho C p V x prime T prime whole average. And similarly, this you can use for other directions as well. Q z, the Reynolds flux, is equal to rho C p V z prime T prime, and Q y is equal to so these are the fluxes in the different directions, because they are the velocities perpendicular to surfaces. Velocity in the x direction perpendicular to a surface in the y z plane and vice versa, and so on. So, this is the heat flux, and then the momentum flux the shear stress, the Reynolds stress tau r tau okay. This is equal to the correlation the momentum density and the velocity. Okay. So, this tau x z is the force in the x direction acting at a surface whose unit normal is in the z direction. So, it is the transport of x momentum in the z direction. Okay. So, therefore, this is going to be the product of rho v x prime v z prime, okay. The correlation in the two components of the velocity. Okay. And I should recall that I had explained earlier that the shear stress is actually the negative of the momentum flux, because the shear stress is considered positive at a surface with outward unit normal in the z direction if it increases the momentum of the volume below, if the force is exerted at a surface whose outward unit normal is in the z direction. In contrast, the fluxes qz and jz are positive if they increase the mass or heat in the volume above. Because of that, the definition of Reynolds stress has a negative sign in it. Okay. So, this is the expression for the Reynolds stress. Okay. So, the physical picture is the same. Okay. So, if I have a flow, okay, I have in a turbulent flow, I have fluids, parcels of fluids moving in different directions. Okay. And if you recall that when we did the molecular description of mass and heat transfer, we took a particular surface and calculated how many molecules are crossing this surface. Okay. Okay. In a gas, it will be discrete transport of molecules. In a liquid, it will be due to cooperative motion and so on. But basically, we are looking at what is the number of molecules crossing per unit time across a surface upward as opposed to downward. And if there is a concentration difference, then we use that in order to find out what is the net flux across a surface based upon the root mean square fluctuating velocity VRMS. Okay. The picture is similar in the case of turbulent diffusion. Here we have to look at what are the parcels of fluid that are going from below to above and the parcels that are coming from above to below, okay, and calculate the flux of mass or heat or momentum on that basis. Now, if you look at a surface within the fluid, okay, let us say that you have a concentration variation with Z. Okay, the concentration as a function of Z, let us say it is a varying function. Okay, the concentration is a varying function of Z. A parcel of fluid coming from above to below will on average have a higher concentration, and therefore, it will carry greater amount of mass down as it comes below the surface. Similarly, a parcel of fluid that is going from below to above will come at a distance approximately what is called mixing length. Below the surface, okay, and therefore, it will have lower concentration, and because of that the net amount, the concentration coming from above to below is higher than the concentration coming from below to above. That results in a net flux. Okay. So, here you are considering parcels of fluid of a certain fluctuating velocity, that is the turbulent fluctuating velocity of the velocity scale v prime, say. Okay. The correlated motion happens over a distance comparable to the eddy size, which is called the mixing length, and therefore, a parcel that is going from below to above is expected to originate at a distance approximately 1 mixing length below the surface. Parcel coming from above to below comes from a mixing length above the surface, and the picture looks very similar. Okay. And on that basis, the expressions that are written for the Reynolds fluxes, the models for the Reynolds fluxes are typically of the form the Reynolds flux in the z direction is equal to minus dr dc by dz, qzr is equal to minus kr dt by dz, where dr and kr are the Reynolds conductivity and mass diffusivity. This is also sometimes written as minus rho Cp alpha r dt by dz, okay, and tau x z r is sometimes written as rho nu r d Vx by dz, okay, where the diffusivities are very similar to what you have for the molecular diffusivities. Okay. So, these are the kinds of relations that are written. Okay. There are a few things to remember about these relations. First thing, in a molecular fluid, the diffusion coefficients, the momentum and mass diffusivities are molecular properties, whereas in turbulent diffusion or in dispersion, okay, in dispersion, these are flow properties. They depend upon the intensity of the velocity fluctuations of the fluid, not of the molecules. So, these are flow properties. The diffusivities are not material parameters, material properties, but they are flow properties. The second thing to remember is that this is an approximation. If you recall, when we looked at molecular diffusion, we had expanded the concentration field in a Taylor series expansion about the surface with the assumption that the molecular scale, the mean free path, is much smaller than the system size. We had subsequently calculated the mean free path and found it to be of the order of 0.1 to 0.05 microns in gases under normal conditions and much smaller in liquids, because in that case the microscopic scale is the molecular diameter itself. So, in both of those cases, the molecular scale is actually much smaller than the system size in most practical applications. In this case, the size of the largest eddies, the mixing length, okay, in the turbulent flow in a pipe, for example, will be comparable to the diameter of the pipe, and therefore, you cannot mathematically expand in a ratio of the mixing length to the system size, because that ratio is order 1. You cannot neglect the second and higher order terms in the expansion. Okay. So, a relation like this cannot be rigorously derived in a turbulent flow, because the length scale of the structures that cause transport are comparable to the system size, and therefore, you cannot do a Taylor series expansion. For that reason, these things have to be necessarily considered as models, not as exact constitutive relations that can be solved. Okay. So, those are the two differences in dispersion as compared to molecular diffusion. Nevertheless, these models for these often express the diffusivities, okay, as some product of some constant times the magnitude of the fluctuating velocity times the mixing length. Okay. Okay, so, this is a constant, this is a model that is used for these these diffusion coefficients, these dispersion coefficients. Okay. They are called turbulent diffusivities, but they are not actually molecular diffusivities, they are actually dispersion coefficients. Okay. So, these are what are called the mixing length models, where V prime and the mixing length, they depend upon the system size and so on. When we discussed gases and liquids, we had estimated the diffusion coefficients as 10 power minus 5 meter square per second in gases for molecular diffusion of mass, and 10 power minus 9 in liquids, and momentum and energy diffusion in gases were also comparable. In a turbulent flow, these dispersion coefficients could be very much larger. Okay. In a turbulent flow, for example, if you have fluctuations of order 1 centimeter per second, okay, which is 10 power minus 4 meter per second. And if you assume that the largest length scale is of the order of 1 centimeter, sorry, this is 10 power minus 2. It's 10 power minus 2 meters, then V prime times Lm is 10 power minus 4 meters square per second, which is much larger than the diffusion coefficients. Okay. This 1 centimeter a second is quite often observed in practice. You could even get much larger sizes. 1 meter a second fluctuations are known in practical applications. And because of this, these dispersion coefficients are actually much larger than molecular diffusion coefficients. And these form the primary mechanism of transport in turbulent flows. Okay. In turbulent flows, the transport is not due to the molecular diffusion, but rather due to dispersion, due to the fluid velocity fluctuations. So, that is a discussion on turbulent dispersion. Okay. There are other kinds of dispersion. Okay. For example, a packed column. Okay. If you have a column of particles, for example, okay, and a fluid is flowing through this column. Okay. If you make an average description where you include, okay, a length scale that is larger than the particle size, okay, as just in an average as an effective medium, okay, as an effective medium, then you have an effective velocity through, okay, but you also have these velocity fluctuations that the particle goes through the tortuous paths between the as the fluid traverses tortuous paths between the particles. Okay. In general, if you have large columns, it is not feasible to describe the flow through each of those around each of those particles. Okay. So, you would like an average description where you divide the velocity into a mean value, which is averaged over some a sufficiently large number of particles that you can use a continuum description, okay, plus a fluctuation as the particle traverses tortuous trajectories between as the fluid traverses tortuous trajectories between the particles. Okay. If the superficial velocity in this packed column is V s, if the superficial velocity is V s, okay, then the fluid velocity through these particles is V s by epsilon. Okay. Why does dispersion take place? Okay, because if the fluid has to pass, okay, a fluid 2 points close to each other that are coming in, okay, as they flow around a particle, they get separated by a distance comparable to the particle diameter. Okay. So, if I had some concentration some spot of dye over here, as it passes around one particle, it will get spread over a distance comparable to the particle diameter, okay, and that is why there is dispersion, okay, because two elements of fluid that were nearby initially, as they go around the particles, each time they go around one set of particles, they get separated by a distance comparable to one particle diameter, and that is what is called dispersion. Okay. So, the dispersion coefficient can depend only upon the velocity V s by epsilon with which it is passing and the particle diameter d. Okay. And just from dimensional analysis, you can see that this dispersion coefficient has to be proportional to by epsilon. Okay, the dispersion coefficient has to be proportional to V s d by epsilon, okay, as the fluid is going around the particles. Okay. That is because the spread in the concentration field over a distance d occurs when the particle travels a distance d. Okay, so, the time taken for a particle to travel the distance d is going to be equal to d by the velocity, okay, d by epsilon v. Okay. And then the the distance that is the spread takes place over a distance over the particle travelling over distance comparable to one particle diameter. Okay. So, dimensionally this can depend only upon V s by epsilon and d, and there is only one combination for this dispersion coefficient. So, it increases proportional to the diameter and it increases proportional to the velocity for the flow through a packed column. Okay. You can derive more exact results for this if you take microscopic models for the particles and look how the dispersion increases as the fluid goes around those particles. But those things they require a more complex description. I will just restrict attention here to saying that the dispersion coefficient increases with the velocity and with the diameter. Velocity is superficial velocity divided by epsilon. Okay. So, that is as far as dispersion in a packed column is concerned. And finally, I will come to the final topic, which is what is called Taylor dispersion. Okay. This is axial dispersion in a pipe flow. Okay. So, if I introduce something a pulse at some location, at some later location I want to know the extent to which this pulse has spread, okay, the extent of spreading of this pulse as it is moving downstream. Okay. And one can consider two situations here. One is if you have what is called a laminar flow, and the second is if you just had what is called a plug flow with a constant velocity across. The plug flow is not realistic, of course. Turbulent flows tend to be more plug like than laminar flows, but the ideal plug flow is not a realistic flow. Nevertheless, we can use this in order to illustrate the concept. Okay. So, in a plug flow, for example, if I impose a spot of dye here, as it moves downstream, okay, it will spread, okay, due to molecular diffusion. Okay, it will spread to some extent, and further downstream it will spread to a greater extent, and so on. Okay. Okay, as this plug flows downstream, it is also diffusing, and therefore it will spread. Okay. And this spread will be according to the molecular diffusion. Okay. So, you can just estimate the length quite easily as the distance just based upon dimensional analysis, as this distance L is equal to square root of d times t, where t is the time taken for the pulse to move the downstream distance, okay, since the injection point. Okay. So, it just goes as square root of d times t. This, on the other hand, in this flow the velocity is 0 at the wall. Okay. It is large at the center. Okay. So, if you look at how this spreads, okay, this will spread something like this. It will diffuse along the length, of course, but the center will be carried further downstream and the wall is stationary. Okay. So, it will spread a much larger distance. Okay. And as it goes further, okay, it spreads over a significantly higher distance still. Okay. So, the convection tends to elongate this initial pulse, and then there is cross stream spreading due to diffusion, and this results in a significantly higher diffusion coefficient when you are at high velocities. Okay. In particular, the diffusion coefficient, the flux, okay, in the flow direction, if I call this as the x direction, it can be written as minus a Taylor diffusion coefficient times dc by dz, okay, where this Taylor diffusion coefficient is equal to the average velocity square, the diameter square, divided by 192 times the diffusion coefficient, or you can also write this as Peclet number square into the molecular diffusion coefficient by 192. Okay. The important point to note is that the molecular diffusion coefficient appears in the denominator here in the expression for the Taylor dispersion coefficient. If the molecular diffusion coefficient is lower, if it does not spread as much due to molecular diffusion, the Taylor diffusion coefficient is higher. Okay. So, the Taylor diffusion coefficient is actually inversely proportional to the molecular diffusion coefficient. So, this action of the convection of elongating and stretching out these concentration variations, and then cross stream diffusion mixing up things in the cross stream direction. This results in an effective diffusivity in the axial direction, in the x direction, whose dispersion coefficient is inversely proportional to the diffusion coefficient. Okay. And this phenomenon is called Taylor dispersion. Okay. So, I have briefly explained to you different kinds of dispersion and contrasted them with diffusion. Okay. So, this completes our discussion of diffusion and dispersion. In the next lecture, we will start looking at unidirectional transport. Okay. So, we will start this new topic in the next lecture. I will see you then.